Okay, I would like to welcome you to the second example. So we are still discussing the moment generating functions, and we have now continued targeting the discrete continuous random variables. So here we are now targeting the discrete random variables. Now, among the discrete random variables, we want to look at this special example. So looking at this question, we are saying if the moment of a variable x are defined by this expectation of x to the power r to be equal to 0.6, and the values that this expectation of x are taking for r are equal to 1, 2, 3 up to infinity, then we want to show that the probability of this function whenever x is equal to 0 is going to be equal to 4. If the probability of x is equal to 1, then it's going to be equal to 0.6, and that the probability whenever the value of x is starting from 2 going upwards is going to be equal to 0. So this is the problem that we have here. Now, from the definition that we have, we've got a variety of definitions of moment generating functions. Now, under the discrete, so what do we have? So the moment generating function of x, in this case, it's going to be given, that is, if you look at the moments, this is going to be given as the summation. Now, our summation is running from 0, that's the origin, up to infinity. And then we're saying t to the power r over r factorial. Okay? And then this is multiplied by mu r. So this is what we have. So this is the moment. So this is a general function, and I'm sure we are familiar with this formula. Now, of course, be reminded that with this formula, our origin is 0, but we have been given a condition that when we are discussing this, the value for r is running from 1, 2 up to infinity. So in this case, if we were to deliberately replace this r by 0, so this is r factorial, which is going to be 1, t to the power 0, which is going to be equal to 1, meaning that we are going to have our mu 0 plus, in this case, this is going to be the summation as r now shifts starting from 1, and then we're going to have t to the power r over r factorial, then over our mu. Of course, our mu 1. Now, our mu 1 is basically whenever the value of x is equal to 1. So in this case, we are going to say our mu 1 when x is equal to 1 is going to be equal to 0.6 according to the problem given. So this is going to give equal to our mu naught at the origin, we'll take it as 1, then summation. Of course, if this number is not affected by, it's a constant, so we could take it out. So it's going to be 0.6. Then 0.6 by the summation of t to the power r over our r factorial, like this. And the r is starting from 1 up to infinity. They are also up to infinity. So now, if you look at the results that we have here, so we know that when the probability given here is given as I take you back, if the value of x is equal to 0, then the probability that we should have is 4. So it's going to be equal to 0.4, because probability of the first one at the origin is 0.4 plus. Then we have 0.6, and then this one is the power series, t to the power r, then r factorial. This is basically the power series which is given as e to the power t. So this is going to give us, so our m of x of t is going to be equal to, so in short, it's going to be equal to 0.4 plus 0.6 e to the power t. So this is our moment generating function. Okay, so we found this. Now, if you look at the question, they want us to show that our result is basically going to prove otherwise up there. So we're gonna move one step further. So now in this case, how do we move? We will use the same definition. We know that, but the general definition of moment of x of the random value of the parameter t is given as the expectation of e to the power tx. Okay, and this is giving us the summation of e to the power tx of the probability of x minus x equal to x. This is the probability function that we have here. Now this one, if you check it, our x is running from 0 up to, we'll say, infinity. This is gonna be equal to, if we replace our x by t, our x by 0, so this is like e to the power 0. If you place, so in short, the first one, if this is gonna be e to the power 0, which is gonna be 1, in short, we are going just to remain with the probability of x is equal to 0. This is gonna be equal to 1. E to the power t times 0. So this is gonna be 1 times this is just gonna be this. And then we are saying our x is equal to 0, which means x is equal to 0 here as x takes on 0. Then plus, I hope everyone is following. Then we take this one, it will be e to the power t when x is equal to 1. Then it will be a probability of our x is equal to x is equal to 1. Then this continues plus here we'll just say, at this point we'll just assume that it continues with e to the power tx, then probability of x is equal to x as x is equal to 2 to infinity, like that. But we know what this one is, so we are saying this is probability of x is equal to 0 plus of course our e to the power t. So if we look at this e to the power t and then we compare, okay, at this point I think we'll just like this one, then probability of x is equal to 1, then plus I will just like this one, our x is starting from 2, sorry, then to infinity, then e to the power tx, the probability of x is equal to this small x. Now I want you to check out this. If you look at this moment generating function which we are looking at now, the last one, this part is basically gonna be equal to this part, and then this part here is basically gonna be equal to this part. Now what does that mean? Okay, the implication are that, I'll write the implications, sorry, it's blur. So the implications are gonna be like this one, which is here. Now I will write probability of x is equal to 0, which is basically this value here, should be equal to this first part here. This part here is supposed to be equal to 0.4. And then if you go to the second part, this one, we are saying e to the power t of e to the power t of the probability of x is equal to 1. Now this one should be equated to this other probability here, which is basically this one, which is 0.6 e to the power t. So if you look at these two probabilities, one thing that should stand out is this one, and this one basically will disappear, implying that probability of x equal to 1 in this case will result into 0.6, and this is the result that we are looking at. But be reminded that from this moment that we were looking at, the moment that we are assuming at the beginning here, we never had anything added here. But if you check what I have obtained here, the result from here and the result from there, when they are added, the maximum value a probability can take is equal to 1. This implies that the probability for the remaining one, that is probability for the values of our x, if they are going to be above 2 or equal to 2, are going to be 0, because the maximum value of any probability gives you 1. That is the addition of this and that. So this shows what we are looking at. Remember, all we needed in this question was to show that the probability of x is equal to 0 is this one, which we have found, when it's equal to 1 is that 1, and anything that is from 2 going up is equal to 0. So this is the solution. Thank you.